This is page 6, number 9. And the setup of the problem has like that. And it says it's attached here at like a roof 50 degrees or here 75 degrees. This is T4, T3, T1, T2. I don't know what the test question asks because they've rewritten a lot of the exam, but this picture being, what it is, they're probably asking you, to compare the tensions. Now, I would assume the comparison is between T1 and T3 and T2 and T4. That would make the most sense on what to compare. Like, how does changing this angle affect these? I mean, just so you know, and I think you guys probably understand this a bit, if we are hanging the same object in both cases, so both of them are supporting this object mg, then in both cases, T2 and T4 are the only cable that is actually lifting the object. T3 and T1 are both pulling to the right and can't lift the object. So just the math of this suggests that there is a component of T2 that is upwards and a component, I don't know if it's that long, but a component of T2 to the right. And T2 actually pulls along that line. It should be clear, though, that the component of T2 in the y direction has to equal mg. It has to. And based on what I'm looking at here, that 50 degrees is also right here. It's this 50 degrees. Suggesting that T2 in the y direction is actually T2 sine 50 degrees. It's got to be the y component. So T2 sine 50 has to equal mg for the y part to balance. Which means that T2 has to equal mg over sine 50. Now, some of you are pretty sharp. What do you think T4 has to equal? Yes? Yeah. I'm sure of it. So, I don't know if you guys know this, but as the angle gets bigger, the sine gets bigger. Right? Because sine of 0 is 0. Sine of 90 is 1. So, T2 has to be bigger than T4. It has to be. And that means, by consequence, that T2 has got to be bigger than T3. I'm sorry, not T2. T1 has got to be bigger than T3. It would have to be. So, the tensions on this side are greater than the tensions on this side. I know that if this angle were 90 degrees, T4 would pull straight up and T3 wouldn't pull at all. So as that angle gets steeper and steeper and steeper, the tensions get less. I think that's what they're getting at in this question. Does that make sense? Now, just so that we're being 100% complete, looking in the other part of this, T2 in the x direction, this part, is T2 cosine 50. I'm just going to be thorough So T2 cosine 50 has to equal T1. That means T4 cosine 75 has to equal T3. Bless you. Okay. A 0.5 kilogram ball is rolled around a vertical circle with a radius of 0.7 meters. All right, so looking down on it, which is what I'm going to kind of do here. There's my circle, and I have to have a... So there's a ball, and it's 0.7, I guess, so. That good? So this is 0.7 meters, and the mass of the ball is 0.5 kilograms. If the speed of the ball at the bottom of the circle is 4 meters per second, calculate the tension. So vertical circle. So we're actually looking at something at the bottom of the circle. I don't know why I drew it like that, so I should probably move. Bless you. That to there. There's that okay? Still mass 0.5, but now it looks like that. So it has a velocity in this direction, for example. So I'm going to draw it. And we're told that this is 4 meters per second. And we want the tension in the string. So the string must be going from here to the center. I foresee that there are probably two forces acting on the object right here. There is tension upwards, and there's the weight downwards. And the tension is going to have to be greater than the weight. This is a net force problem with a centripetal acceleration, which means the only way this object travels in a circle is if the unbalanced force is equal to MAC. There are two forces that act on the object. There's the tension, which acts upwards, and the weight, which acts downwards. But I want the acceleration to be upwards, so the object travels in a circular path that arcs it back upwards. So I need the net force to be positive, because I'm setting upwards to be positive. That means this must equal mv squared over r. Solving for tension, I get tension equals mg plus mv squared over r. Now there's a numerical answer here. We were told the mass was 0.5, so this will be 0.5 times 10 plus 0.5 times 4 squared over 0.7. All right, there's a number here somewhere. 0.5 times 10 is 5, plus 4 squared is 16. 16 divided by 0.7 is, I'm sorry, what? 22.85, so half of that is going to be 11.425 or 11.43. So 16.43, is that right? Newtons. Yeah, this can be on your exam. Every bit of this can be on your exam. There's no reason to think it can't. Question B, what is the minimum speed to maintain the ball on the circle at the top of the path? Don't know if that's on your exam, but we should be able to do it without an issue. Now, this question changes the calculus a bit. So I want to kind of start fresh real quick. I'm going to take some of this stuff and get it out of here, so we can kind of start fresh. The ball is going to be at the top now, and it's experiencing, still has a cable here, and it's still moving to the side apparently at 4 meters per second. And we want the minimum speed, so we don't know how fast it's going to the side. So V is unknown. We want V minimum. To do this problem, we have to consider what's happening to the ball. And again, there are two forces acting on it, tension and weight, and they both act downwards. I need the ball to have a downwards acceleration for it to travel in a circular path. So I will make downwards positive, and I'm going to state that the net force is equal to MAC. There are two downward forces and they point in the same direction. Tension plus weight equals mv squared over r. Now, here's why this problem is different. We are not given a velocity and asked for the tension. We're asked for the minimum speed for it to make it over the top. Now, the speed that it has to travel at is based on how much force there is acting on it. So for it to make this turn, the minimum speed will be based on the smallest force that it can experience there. Well, the tension can pull as hard as I want, unless the string breaks. But the smallest force is as the tension goes to zero, because the weight of the object isn't changing as you spin it. The weight of the object is staying the same all the time. So if we assume that the weight of the object is a constant, the only one of these things that can actually get smaller is tension. So the minimum speed is when the tension is gone, and all I have left is mg. Minimums and maximums tend to be when a reactive force goes to zero. So normals and tensions are reactive forces. They react to the conditions of the problem. So I'm going to cancel out the m's, solve for the v min, and I get v min squared equals r times g. So v min equals the square root of r, which is 0.7, times g, which is 10. So the square root is 7, which is about 4. What is the square root of 7? 2.6 what? Bless you, 2.6 meters per second. If it goes any slower than that, then it doesn't travel in a circle. There'll be slack in the string and it'll just fall kind of downwards. It'll basically fall like that. So it'll just slacken up the string some. This can be on a test. I kind of hope not, because students tend to trip up on this. But keep in mind, if it is, it's a longish question. Budget your time for it, because you have to do all this. There's no shortcut here. I will say that R is in meters and G is in meters per second squared. One way to check if you're doing it right, do the units work out. This gives me meters squared per second squared under the radical. So my answer's in meters per second. That's good news. Means I did my algebra right. Alrighty. Nobody? 385,000. Good enough. Joules. All right, so this is how much the car's kinetic energy changed. That's a big change in kinetic energy. This is also how much work was done by the engine on the car. If I want the efficiency of the engine, I'd have to take this number and divide by the energy that was released when we burned the fuel. And we burned 1.76 times 10 to the 6th joules. It's 10 to the 3rd kilojoules, so it's 10 to the 6th joules. This is the efficiency of the engine. Work out divided by energy in. I would not expect you to be able to do this question on the exam. I don't expect this question to be on the exam. However, question A, I'd like you to be able to do, because we talked about the definition of power. And the definition of power is work over time. So this one I do expect. The car did 385,000 joules of work, and it did so in 4.6 seconds. This quotient is the amount of power the engine supplied to the car. And although I don't have the answer, I'm sure you can figure this out. The answer will be in watts. They shouldn't list it as joules per second, but they could. But a joule per second is a watt. These are the same unit. You can divide that out and get your what? I think we're talking about probably 90,000 watts or so. Maybe less. Lauren?
Is work and network, they're two different things, right?
Yes.
Isn't the change in kinetic energy equal to the network?
It is. But in this problem, we have no information about individual forces doing work on the problem. The only thing we have to go on is the network that acted on the car. Generally, when we're talking about power or efficiency, we are also only talking about the network. Generally. I mean, it doesn't have to be true. But, the car being accelerated suggests that we're dealing with net work on the car. Now, we have two definitions for power. Work over time and force times velocity. In this case right here, the net work could be zero. The car could be traveling at a constant velocity. We'd be talking about the force used to maintain the car's velocity. So that, you're right. In this case, we wouldn't be able to do it. But we have no other information to go on in this problem. So we'd have to use the change in kinetic energy to calculate the power. C, what happened to the missing energy in this case? Who knows? Sound, friction, heat. I mean, you guys realize that your car is terribly inefficient. So electric cars are much more efficient, but if you're burning gasoline, most of the useful energy is probably being exhausted as heat. It's being exhausted as particulate matter. It's being exhausted as sound. All of that stuff that you guys, that's leaving the car, that's not contributing to the car moving. Those things are where all that energy is going. So, yeah. Just this chemical process of burning the fuel, unfortunately, creates new elements and new compounds. The creation of those new compounds is wasteful, wasting energy. All right, so this is page 5, number 5. All right, a ball is released from the top of a curved hill as shown above. The hill has sufficient friction so the ball rolls as it moves down the hill. So it doesn't slide, it rolls. What can be inferred about the ball's linear acceleration and speed as the ball goes from the top to the bottom? Increase, decrease, or remain the same? Well, the linear acceleration of the ball is going to decrease because the slope is getting shallower. So when a slope is very steep here, it's going to have a greater acceleration. Remember, the acceleration is going to be based on mg sine theta. And I know you guys aren't proficient at this, but the steeper it is, the greater the angle. Sine increases with angle. So, as the angle gets bigger, mg sine theta gets bigger. That has to equal ma. So if it's steeper, it's going to accelerate more. So this object's acceleration starts large and gets smaller. The speed, on the other hand, is always increasing. The speed's always getting greater the whole time. It's not getting greater as quickly at the end as was at the beginning, but it's always getting faster. You will mess that up. You'll somehow think that it slows down, but it never slows down on this ramp. It always speeds up. What's funny is that if the ramp were instead of what we see here, what if the ramp were this? This question was on the exam a couple years ago. I don't think it's on it this year. This is the opposite, right? It's going to accelerate slowly in the beginning and quickly towards the end. So if you have a ramp like this put next to a ramp like this, and they're the same height, which ball is going faster when it reaches the bottom? trick question. Neither. Energy should be the way to go here. Is the height any different between one ramp or the other? No. So they change the same height, they'll have the same velocity, because they're going to have the same kinetic energy now. But which ball gets there first? The ball on the right. Because it accelerates faster in the beginning. So it'll reach its top speed sooner. So it'll make it to the bottom sooner. I haven't asked that question in a couple of years, but it could be back this year. If we have this picture, it could be back this year. I didn't see one that had a comparison of the two, but, it's a neat question because it makes you really think about the difference between acceleration and energy. All right, so there's a collision that has, a small object striking a very large object. My recollection from last year, because I don't remember, I didn't have time to read the exam, but is that it's like a small nucleus strikes a big nucleus. They give the masses of everything, and they give the initial velocity, and they want to know the velocities after the collision and stuff. If it's an elastic collision, they say it on the exam. Look, you're short on time. It might just be better for you to test the answers than solve for it. Do you understand? Because you'll make mistakes solving for it that you won't make if you're just testing. So they've got to give you, let's say it's like this question where they give you that this is m, and they give you the velocity here v, and this is 9m, and they're interested in what happens during this collision. And so afterwards, who knows, maybe this is that way, and this is this way. I don't know what the answers are going to be. But they're going to have, they're either going to give you one of these, or they're going to ask for both of them. That's really a hard question to do in a couple of minutes. But my assumption is that A, B, C, and D are going to contain two different velocities, or at least they're going to contain the two answers. If it's just a collision, then you know that the mv here has to equal mv plus mv here. So rather than solve for it, test. Take the two velocities, plug them in, and see, do they equal what you had in the beginning? Now, that would probably be one where it's about the same amount of work, unless they say the word elastic. They say the word's elastic, then this also has to be true, in which case solving for it is harder. So I would just test the answers till you get the right one. That's bound to be faster. So if you have an elastic collision question, look, you just have to know that the kinetic energy is equal before and after. That's a good thing to test. They might have two or three there where the momentums are equal. Just test the kinetic energy. Find where the kinetic energies are equal. Boom, you know. Be careful though, they could have the original velocities as the answer, and that would not be the right one to choose. Do you one better? Page 1, number 1, first. A lot of people don't understand what they're trying to do here, okay? And it says, a student wants to determine the height of an unreachable object. The materials available include a protractor and a tape for measuring small distances. Describe a procedure that can be used to achieve the objective and what quantities can be graphed to determine the height of the object. We teachers hate this question, meaning the people that I work with hate this question because it's, as a multiple choice question goes, it's tough. We're talking like the idea that you're going to measure the height of a flagpole or the height of like the lift hill on a roller coaster where you can't actually measure it. What they're trying to get at with having the protractor is something that you can measure. And I'm doing this question because it's on page 1 and we're back to page 1. What they want you to do is say, okay, I'm going to measure a distance along the ground because I am too short to reach the top of the flagpole. I'm going to stand at this distance with my protractor and measure the angle from here to the top of the flagpole. and I will use this distance and this angle to predict the height of the flagpole. Probably using, I don't know, tangent of the angle will equal y over x. So if you wanted to graph something, you would measure lots of different x's and different thetas and plot x and tan theta. That's how you would do it. They can't do all that on a multiple choice question, though. They can point this out on a multiple choice question. An object is dropped on the surface of a different planet where the acceleration due to gravity is not 9.8 meters per second squared. The object free falls a distance 2.3 meters in 1.2 seconds. Calculate the acceleration and velocity of the object before impacting the ground. Assume no friction. This problem, it's suggesting that there's an acceleration downwards that we don't know. But we do know that the object falls a distance of 2.3 meters and it takes 1.2 seconds. So I'm thinking delta y is negative 2.3, vy naught is 0 because it's dropped, and we're looking for the velocity it strikes the ground and the acceleration when the time is 1.2 seconds. So to me, motion equation is the best way to go here. If I want the velocity, I would use everything here except for the acceleration. So that's going to be I have to pull the equations out. Delta y equals 1/2 times v plus v initial times t. I am not using the terms that we used in your class. We used final and initial there. So that'll give us final velocity. And then when I'm searching for the acceleration, I would probably use delta y equals 1/2 a t squared plus v initial times t. That's where I'd go. You get that one's not on the motion, that's not on the equation sheet. So, you can get it from other stuff. You could solve for the acceleration first then and get it. But, you could memorize it too. It's your call. I'm not sure how much value there is in memorizing that. A water rocket has a total mass of 500 grams before launch. Upon launching, air pressure blasts the water out the bottom, propelling the rocket upward with an average force of 40 newtons that lasts for 0.5 seconds. That tells me impulse right there. So, if the rocket hits 100 meters per second, what mass of water was ejected during the launch? All right. I know it sounds like we've never done a problem like this, but let's see what they gave us. Force times time equals m final v final minus m initial v initial. Clearly the rocket's mass changed. So I'm going to put final initial for the mass of the rocket. I know that the force on the rocket was 40, and it did that for 0.5 seconds. I know the rocket started with an initial mass of 0.5, but the initial velocity was 0. And I know the final velocity of the rocket was 100, but I don't know the final mass of the rocket. Do you see where I'm going here? Now, this will tell me the mass of the rocket after the rocket engine is fired. I'll get 0.5 times 40 is 20, divided by 100 is the mass of the rocket. So that's 200 grams. But the rocket had a mass of 500 grams, so how much water was ejected? 300 grams. Bye, guys. Have a great day. Again, this is page 1, number 1. It says that a student wants to determine the height of an unreachable object. They want to describe a procedure to do so. And best fit line. I'm not exactly sure what they're getting at, but let's assume that maybe that's what we're talking about here. The idea here is, how do you measure something that is taller than your measuring device? So if you have like a flagpole and you want to measure its height, and you don't have a tape measure or a way to access that height, then something you could do instead is you can measure a distance away from it. They say you have a protractor, so it seems to me you could also measure this angle. Now with that information, you should be able to determine the height by using trig. It seems to me tangent of the angle should be equal to y over x. Now, they suggest that, you find a way to graph your data in order to get this height. So you could graph this data in order to get the height. To do so, you would probably have to do something to x and tan theta to graph it, so that the slope is y. Probably the best way to do that would be to remember that y equals mx plus b. So for this problem, tan theta equals y times 1 over x plus 0. So I would graph 1 over x on one axis and tan theta on the other. The slope of this should be y, the height of the flagpole. I think that's what they're getting at in this question. All right, so it's the other exam review. Number 4 says 2 vectors lie with their tails at the same point. When the angle between them is increased by 20, their scalar product has the same magnitude but changes from positive to negative. The original angle was, this is not a physics question, and a lot of people asked about it. I gave them the answer because it's not a physics question, but they're trying to get at something, and so let's make it about physics, since I know there's no chance in heck that this is actually on the exam. The only scalar product we talked about was the one that has to do with work being done. That work was the scalar product between the force and the displacement, which meant that work was force times displacement times the cosine of the angle between them. So the vector product is based on cosine. That's ultimately what it comes down to. They would like to know what angle has the same cosine, but one's negative and one's positive, and they differ by 20 degrees. Well, as I look at the angle here, I realize that you will reach a point where the angle between F and delta x will get close to 90 degrees. At 90 degrees, cosine is 0. So effectively, the vector product here would be 0. There's no part of the force in the direction of motion. But I do know that if the force were just a couple of degrees smaller, there would be a part of the force in the direction of motion. And if the force was a little bit greater than 90, we would now have a component of the force against the direction of motion, which would make the vector product negative. So if these are separated by 20 degrees, what would center them at 90? Do you know the answer?
can't see. I'm trying to look around you.
So if the green F and the blue F are both the force part of the vector product and delta X is the other part of the vector product, then you'll notice that the green F has a positive component in the direction of motion, and the blue F has a negative component in the direction of motion. They have to be separated by 20 degrees. What angle does that put it at?
90.
No, because this one's 90. So I'd have to have 10 degrees before it and 10 degrees after it. So it's 80 and 110. Put them both in your calculator, you'll get the same answer, but one's positive and one's negative. No, I'm sorry, you're right, 80 and 100. All right. So I have some picture here. They tell me that there's a girl who's got some spring launcher that's going to launch an object off the top of some bricks. It's going to land somewhere on the ground. And all we know is the height of the bricks is 20 centimeters each. We don't know the height of the table. And we don't know how fast they're shot, but we have data points that will tell us where it lands on the ground with a certain number of bricks. And you want us to use that to figure out h and the velocity that they're shot at. All right. Sure, there's no chance of this being on a multiple choice test. Okay. It's not wasting my time. I can pass the exam. So D is 0.42, 0.48, 0.54, 0.59, 0.64. This corresponds to 0, 1, 2, 3, and 4 bricks. Occurs to me that there are several things that we can put together here. First, as I've told you guys before, the time it takes something to reach the ground is the square root of 2h over g. I think that's going to be useful here because the range equals vx times t. Now, again, I don't really believe that this is the way it's going to be on the exam. I can't. But I can solve this question using what's here. It's going to take a little bit because the range equals vx times the square root of, and I'm going to change just a little bit because h is actually h plus the number of bricks times 0.2. So I need to write this a little bit nicer. So h plus number of bricks times 0.2. All divided by 10. Well, you have Vx is an unknown, h is an unknown, but you have lots of cases of having this number, which is number, and d, which is actually the range. Now, I assume they don't want you to just plug these in, that they want you to graph it. So maybe graph it to figure out Vx or graph it to figure out h. I'm not going to do that because it's a waste of my time. But I could put in, say, this data point and create an equation. That'd be 0.42 equals Vx times the square root of 0.2 times h plus 0.2. 2 divided by 10 is 0.2. And I could put in, say, I don't care, how about this data point? 0.59 equals Vx times the square root of 0.2 times h plus 3 times 0.2. That gives me two equations and two unknowns. I'd probably solve for Vx, set them equal to each other to get h, then go back to get Vx. It's not ideal. Ideal would be to plot this data, but we don't have that kind of time. It's a multiple choice test. Next question. All right. An object is launched at an angle of 45 degrees from the ground of a mystery planet. The object hits the ground 20 meters away after a total flight time of 4 seconds. Assume no air resistance. What are the initial vertical and horizontal velocities? So this is page number 3, number 15. Now, this sounds like a projectile problem. I'm not sure how much of it really is. First, the initial y velocity and Vx have to be equal because they're launched at 45 degrees. So that's just because they used 45. If they used some other angle, that would not be so straightforward like. But because they used 45 degrees, the sine and cosine of 45 are both the same. So I know that's playing around in the back of my mind. I also know that I could write out the whole projectile motion stuff. Which, yeah, there's going to be projectile problems on the exam. I'd be able to do them. Again, Vy naught and Vx have to be the same, but we have some data here. We're told that the range was 20 meters, and we're told that the time was 4 seconds. Well, range equals Vx times t, so that means Vx is 5 meters per second. Because I can do the math, I think you guys can too. 20 divided by 4 is 5. And since it was 45 degrees, that means Vy naught was also 5 meters per second. Because the angle is 45 degrees. If they gave me a different angle, you'd have to do some math to figure out how they're related. I'll remind you that Vy naught is the launch velocity times the sine of the angle, and Vx is the launch velocity times the cosine of the angle. So if they gave us something other than 45 degrees, this might be harder. But 45 degrees means no work here. Yep?
Can I just clarify? So, if we didn't have the angle that was...
So, the next part of this problem reminds me that this object is, they want the acceleration due to gravity. This object launches and lands from the same height, which means the delta y is 0. It's in the air for 4 seconds. I should be able to use this to figure out A. So that's what I'm going to do next. Because it says what are the initial velocities, next says what's the acceleration due to gravity. So I'm going to use a relationship that uses everything except for final velocity. That'll be delta y equals 1/2 a t squared plus Vy naught times t. That'll be 0 equals 1/2 a times 4 squared plus 5 times 4. So this will be negative 8a equals 20, or a equals negative 20 divided by 8. which is, 2.5, I think. The negative sign means downward. So that's question B. Nothing wrong. This is all fair game on the exam. Question C. Draw graphs to quantitatively represent the vertical and horizontal velocities for the entire 4 seconds of flight. But looking back here, the vertical velocity starts at 5, but has a slope of negative 2.5. That's if you're actually supposed to plot the velocity versus time for both things. And that's kind of what they say in this question. It says, draw graphs to quantitatively represent the vertical and horizontal velocities for the entire 4 seconds of flight. The only way they can do that on a multiple choice test is to give you several examples. But I know students, they sometimes don't look at all of the examples. And I know from flipping through your test, a lot of you didn't write this out. But I know that if this is the velocity and this is the time, then there's one for the vertical and one for the horizontal. The horizontal velocity was 5 meters per second. It never changed. So that's the horizontal velocity. It never changed, so it should be a horizontal line, just like so. There's a graph over here for the vertical velocity that starts at the same place but ends at the negative of the answer. So maybe like that. That's what I would expect it to look like. It says to make it quantitative, so you should probably get in there and make it quantitative. I know that this is at 2 seconds. This is 4 seconds. This should be -5. This is 5. And yeah, you should know why. All right. Got some graph here. Maybe that's pretty rough. Let's try that again. All right, the graph looks something like this. I don't want to spend a lot of time trying to get it just so. That's 1, or no, it's 2, sorry. That's 2 seconds. This is supposed to be 4 seconds. This is supposed to be 6 seconds, and it starts at 0, and this velocity here is 4 meters per second. And I'm supposed to calculate the average velocity and average acceleration from 0 to 4 seconds. Well, the average acceleration is 0. And I'm pretty confident. It has a positive acceleration for 2 seconds of 2 meters per second squared. Has an acceleration of 0 here. An acceleration of -2 meters per second squared here. I'm supposed to figure out the average acceleration from 0 to 4. Then that would be the total change in velocity over the total time interval. Well, the velocity starts at 0 and ends at 6. The velocity starts at 0, ends at 0, and the total time was 6 seconds. So the average acceleration isn't particularly interesting. If you don't like that, when you split it up into 3 parts, and find the weighted average of these three values, you end up getting a 0 again. Now, we don't have a word for the scalar part of acceleration. If we did, there'd be an answer to that. But we can get an answer to calculate the average velocity for the, it says from 0 to 4 seconds. And the whole thing is 6 seconds. So there is a different answer then for the average acceleration, because I'm only interested in this part. So that's a bit of a cheat, but if you don't read your test closely like I just did, you'd be kind of screwed. Here, the final velocity is 4. The initial velocity is 0, and time interval is 4 seconds. So the average acceleration would be 1 meter per second squared. That's the change in velocity over the change in time. That doesn't really tell us what happened, but that'd be the answer. The average velocity over the interval would be the total displacement of the object. So I'm going to need the area under the curve here to get the total displacement. So I'll break this up into two sections, this section and then this section. This section has a displacement of 4 times 2, or 8 meters. This section has a displacement of 1/2 times 2 times 4, which is 4 meters. So I have a total displacement of 12 meters. Total time interval of 4 seconds. So the average velocity will be 12 meters over 4 seconds, or 3 meters per second. Calculate the force acting on the object from 0 to 2 seconds, 2 to 4 seconds, and 4 to 6 seconds. Well, since I already found the accelerations for each of those, it should be pretty easy to find the force, since net force equals ma, and we're told that the object has a 3 kilogram mass. Seems like the net force in the first 2 seconds will be 3 times 2, or 6 newtons. And the second part will be 3 times 0, or 0 newtons. And then the last part will be 3 times -2, or -6 newtons. So that's number 16 and number 17. Okay, this is page 5. Number 7 and 8. 7 and 8. The first instance of this problem has just a force of 30 newtons pulling down on a 3 kilogram box. The acceleration of this system is 10 meters per second squared. I don't have to do any work. And the reason is because there is a single force acting on the box of 30 newtons. There's a single box that is moving, 3 kilograms, times A, F equals ma. So A is 10. This is not an Atwood machine. But don't get complacent, because they immediately replace this with a box of weight 30 newtons. They're trying to actively trick you. A box with a weight of 30 newtons has a mass of 3 kilograms. You see that, why that's true, I hope. Because mg would give you the weight. 3 kilograms times g should be about 30. This problem is the actual Atwood machine and will not have an acceleration of 10. That's because the net force on the system is 30 newtons. But the mass of the system is 6. So the acceleration here will be 5 meters per second squared. However, since most of you need more than that to do this problem, I'll remind you that the box that is hanging is experiencing two forces, 30 and tension. If I choose this way to be positive, then that will be 30 minus tension equals 3A. The box that's on the table is experiencing one pulling force, tension. And it's pulling in this direction. That has to equal 3A. The A here and the A here have to be the same because they're connected by a single light string. So when I do my substitution, I'll get 30 minus 3A equals 3A, or 30 equals 6A. That means the acceleration is 5 meters per second squared. I suspect that something like this is on the test, or they wouldn't have asked it here, or they'll just have a straightforward Atwood machine question with two different masses. That's fine. It does ask what will happen to the tension on each body. Well, the tension was 30 newtons before, because they're just pulling down with 30 newtons of force. Here, however, the tension is different. Tension is less than 30, because it has to be. If the tension was 30, then the net force on the box that's hanging would be 0, and it wouldn't go anywhere. That's unreasonable. So I know that the acceleration's 5, so here the tension would equal 3 times 5, or 15 newtons. Also, if I plug that in here, I'd get the same answer, that the tension would be 15 newtons. Page number 1. Page number 1, number 5, 6, and 7. Something like this, with this part being section A, this part section B, and this part section C. It says for segments A, it's going at 25 meters per second for 3 seconds. Section B is 35 meters per second for 4 seconds. And section C, 30 meters per second for 3 seconds. So just real quickly, this is 75 meters. This is 140 meters. And this is 90 meters. Is that right? All right, so it says calculate the average speed of the car over the 3 segments. The average speed would be the total distance traveled by the car divided by the total time that it traveled that distance. So for question number 5, it would be 75 plus 140 plus 90, all divided by 3 plus 4 plus 3, which is going to be 10 seconds. So let's see, that's 205? 305. Okay, 305. In 10 seconds, or 30.5 meters per second. That'd be the average speed, which is weird because you couldn't do question 5 without knowing question 6, which is the distances for each segment and total distance. Because if you find the averages, that won't give it to you. So if you average 25, 35, and 30, you won't get the right answer because you needed a weighted average. It was based on how long it took. So number 6 you had to do already, and it's up there. Number 7, qualitatively distinguish between total distance and displacement. And displacement is path independent. That's the biggest difference. Displacement is your final position minus your initial position. But distance recognizes how far you've actually traveled. That's how they are different. All right. Next question. So I have a larger rock thrown with some horizontal velocity, and this rock lands 20 meters away from the base of the building, while a smaller rock thrown with a different horizontal velocity lands 40 meters away. Well, it says qualitatively compare the time of flight for both rocks. They're the same. Both rocks fall the same vertical distance from the height of the building. It doesn't matter that one rock is more massive or less massive than the other. The time of flight is really dependent on the horizontal property, which in this case, since it has no vertical velocity, the time of flight is going to be the square root of 2h over g. And we've talked about this quite a bit. So both rocks will hit the ground having traveled for the same amount of time. On the other hand, since the range is equal to Vx times t, and both rocks hit the ground with the same time of flight, the one that traveled further horizontally had to be the one with the faster horizontal velocity, because the horizontal velocity is the range divided by the time. So I think we can plainly see that the rock that traveled twice as far must have been thrown twice as fast. It says, compare and contrast the vertical and horizontal components of each rock. The vertical components of each rock, assuming we're talking about the velocity and acceleration, the vertical components of velocity would be the same for both rocks. They both start with a vertical velocity of 0. So the initial vertical velocity of each rock was 0 because they were thrown perfectly horizontally. They both were accelerated downwards by the acceleration of gravity. And that was the only thing accelerating them throughout the course of their flight. So they both experience the same vertical acceleration. The only thing that separates these two rocks is that one of them was thrown with a faster horizontal velocity. But the vertical part of the rock's flights were the same. Now, the horizontal velocities were different, but it's important that you recognize that the horizontal velocities never changed. So Vx for the rock that went twice as far was the same the entire flight, as was Vx for the other rock. It never changed. The horizontal velocity isn't accelerated by gravity, so it stayed the same the whole time. Is that good, Kyle? All right. So I think this one is very relevant to the test. It says a spring-powered launcher is used to accelerate a 100-gram pinball from rest to 6 meters per second on a level surface. Find the work done on the ball by the launcher and the force constant of the spring. So that's A and B. So let's handle A real quick. The launcher starts compressed some distance. Actually, it's 5 centimeters. And at this moment, the ball has no velocity. The spring launcher is released, and the ball travels away from the spring launcher at 6 meters per second, which suggests that right here, the ball had a change in kinetic energy. So the work done by the spring launcher has to be equal to the change in kinetic energy. That'll be 1/2 times 0.1 times 6 squared, 1/2 mv squared, minus the original kinetic energy, which is 1/2 times 0.1 times 0 squared. It was launched from rest. Don't be complacent about the initial velocity and final velocity. If they're moving when they have the work done, you need to make sure you realize it's the change in kinetic energy. That's an easy way to mess you up on the exam. I don't think they're going to try and do that, but I just want to throw it in there. Now, 6 squared is 36. Half 36 is 18. 0.1 times 18 is 1.8. So 1.8 joules is the work done by the spring on the ball. We're next asked to find the force constant of the spring, assuming it was initially compressed 5 centimeters. Well, the energy stored in the spring is equal to 1/2 kx squared. We know this has to equal 1.8 joules because this was the energy that the ball had as given to it from the spring. So I'm going to assume the spring had this energy beforehand. Any question about that? Conservation of energy. So this has to equal 1/2 times k times 0.05 squared. Um, 0.05 is 0.0025. Trying to do this in my head. Is it 1440?
Yeah.
That's newtons per meter times K. Oh, lucky guess, I'm sure. So that's a spring constant. Any question about where I got that from? Alrighty. So it says if the launcher were fired straight up instead, how high would the ball go? I don't really think I have to do any more work with the spring part, except to understand that if it was turned on its side to be launched straight up, if we assume it was compressed the same 5 centimeters, then the amount of energy I would have here would be all elastic potential. And then when the ball is shot and goes up to here, this energy would be converted into gravitational potential. Does that make realistic sense? Any question about that? Well, if the energy is conserved, then there was still 1.8 joules of energy in the spring. If we assume this is the lowest part of the ball's motion, then it will rise to a height where the gravitational potential energy is 1.8 joules. So I think we'd say the elastic potential energy will equal the gravitational potential energy at the maximum height, which will be 1.8 joules equals mgh, where this is 0.1 times 10 times h. So h is 1.8 meters. Now, I don't know how they asked the question. If the launcher were fired straight up instead, how high would the ball go? Well, from the lowest point, it's 1.8 meters. If we have to take that 5 centimeters into account and it's the height above the launcher, then subtract 5 centimeters. But I don't think they're trying to trick you here. I think the answer is 1.8 meters. Both of you had your hands
I
up.
just have a question.
Okay.
What do we use for gravity? 9.8 or 10?
That's a good question. Let's go with 10. I don't know the answer. So I am sure within the first 2 or 3 questions, we'll know. Does that make sense? By the time you take it, I will have already known. 5th period will have endured that. But my recollection last year is that it was 10. But look, you don't get much of a different answer if you use 9.8. So it's going to be, the answers aren't going to vary by whether you use 10 or 9.8. That was question C. Just like this was question B, and this was question, I guess, A. So question D is the launch speed of the ball if the same spring launcher was compressed 50% further. Okay. That's going back to question A, really. So I'm going to do that again. but it's 1/2 kx squared is going to equal 1/2 mv squared. The spring energy will be set equal to the kinetic energy. That'll be 1/2 times 1440 times 0.075 squared equals 1/2 times 0.1 times v squared. There's no easy way around this. You're going to have to do all of this to get the answer. So, can I leave that to you, or do you want to get the number? If you want to get the number, I'll wait a second because I see people pushing buttons.
It's 9.
And I'll just wait. What does he get?
I got 9.
9?
Exactly.
Let's see if somebody else gets 9. I think it will be.
9.
Because the displacement is squared and the velocity is squared, any change in displacement should be reflected by that change in velocity. So it's a 50% increase. It was going 6 meters per second before. The 50% increase would be 9. But it's always best to work these out if you can. All right, that's number 14, A, B, and C, and D. Any follow-up questions about this? This is definitely on the exam. All right, so we have a graph. This is a force that varies with distance as shown on the graph below, acts on a 500-gram object that is free to move without friction on a horizontal track. How much work does this force do over the first 3 meters of the displacement? Folks, read those carefully. Our graph goes to 6 meters, but they only asked about the first 3 meters. It's an easy way to trick you on a test, especially since the next question wants the whole interval shown. So if they start screwing with you like that on the test, it's an easy way to trip you up. But they're specifically asking in this question for the area under the curve, because we want the work done, and we have force and displacement on our axes. So the work is going to be the area under the curve, because force times displacement is work. So question A, I'm going to do 1/2 base times the height. And this gives me 15 joules of work. B, what is the total increase in kinetic energy for the object over the interval shown? Well, work is the change in kinetic energy. So if we assume that, we're just looking for the change, that's no big deal, but we want the whole interval shown. So now we want the area under the entire curve. So that's going to be 1/2 times the base times the height, which is now 30 joules. And this will equal my change in kinetic energy. This problem is asking specifically about the 3-meter interval. So the work done in the 3-meter interval changed the object's kinetic energy. And it changed it by 15 joules. Because that's how much work was done in the 3-meter interval. But that's 1/2 mv final squared minus 1/2 mv initial squared. And it has an initial velocity. Look, if I was writing a test, I would definitely put one of the answers in there as assuming it started from rest. So if I were you, please don't be complacent. Work is the change in kinetic energy. Be aware. I was just talking about this on another question, and here it is right in front of us. So this is going to be 15 equals 1/2 times 0.5 v final squared minus 1/2 times 0.5 times 1 squared. Now, unfortunately, this is like a ridiculously small number compared to what the other one's going to have to be, because half of 0.5 is 0.25. So this is going to be 15 equals 0.25 v final squared minus 0.25. So I add the 0.25 to both sides, solve for v final squared, and I'll get,
7.8.
is that what it is?
Yeah.
7.8 meters per second. All right. Yeah, that could be on the test. There's absolutely nothing wrong with it. It's just long. So hopefully it's at least broken up into multiple questions. But that could be on the test. And they could ask just C. And that would be okay. Next question. Instead of doing the whole problem, I'm going to set it up, but I'm also going to talk to you about what I would do if this was actually on the test. And look, I don't know if there's going to be an elastic collision on a test, and let me hit pause. Here's what I want you to consider. If they say it's elastic, in this problem we have an object that's small, m, striking a stationary object that's 9m. This could be the way it is on the exam. If it's an atom kind of question, they could just give you the atomic units, and that's still just like m and 9m. After the collision, though, I don't know what the two objects are doing. We don't know what their velocities are, v1 and v2. I'm just assuming that the little object bounces off the big object, but I don't really know. I know that it's going to be m times v plus 9m times 0 equals m v1 plus 9m v2. Now look, this problem gives us no numbers in which to work. That's kind of rough. All we've really got is 9 and v. That kind of stinks. But we are told the problem is elastic, which means that 1/2 mv squared plus 0 equals 1/2 m v1 squared plus 1/2 9m v2 squared. Solving this for v1 and v2 is hard, really hard. It's a lot of math. There are shortcuts, but it's still a lot of math. One shortcut is, as you can see, to just cancel out the m's, which will give you v equals v1 plus 9v2. And then the next one, cancel out the 1/2 m's, which gives you v squared equals v1 squared plus 9v2 squared. It's still not easy to figure out what to do next. You've got to do some substitution and stuff like that. But don't do this on the exam. If you want the easy way to the answer on the exam, look at A, B, C, and D. They're going to give you the velocities. When you look at them, just test them. Put them back into the equations and see which ones add up and which ones don't. It's really fast that way. All right.